Hello everybody, welcome back to my YouTube channel. In the last video, we took a deep dive into encoder decoder model and its architecture, and everything was covered in detail in that video. If you haven't watched that, please go and spend some time on that. In today's video, we will understand what attention mechanism is and why do we felt the need of this mechanism when we already had encoder decoder model. So the reason was that since the output that is coming from here, it's a vector, right? And we call that context vector. Now this context vector is going as input inside our decoder, and this decoder is then decoding and giving us output on the basis of this information that it has got. Now this is a very small sentence, right? This is an apple. But consider scenarios where we have paragraphs, documents, something which is more than 25 words. Now, if such big sentences are being passed in inside our encoder, do you really think that this vector will be able to represent every information that it has got? No, right? Because this context vector is only compressed representation of whatever you have got inside your encoder as input, right? It is compressed representation, or if in other words I should put it as summary of whatever you have provided as input. Now this summary can't be entire representation of what you have passed as input, and since this is summarized information, what you are getting as output from your decoder is also based on that incomplete information, right? So your encoder decoder model does not perform well when you have long sentences, something with words more than 25, right? So in those cases, encoder decoder model fails. It would have been better that somehow we can pass the information that, for example, in order to translate this word apple and get save as output, if somehow we can pass this information that in order to get output save, this hidden state which we are getting from apple input is the most important one in getting save as output. Or it would have been better if we can provide only those necessary hidden states that are actually helping in translation or providing that output, because that is how we humans also translate, right? If we are given a very long story and we are told to translate this in any other language, then how we translate that, we look only at a certain portion and the context around it. We don't look at the entire story and then translate it, right? We only look at certain parts and the context around it, and then we do the translation. Same here, this entire sentence is not important to get save as output, right? To get save as output, the most important input is apple and the hidden state that we are getting from here. Same way, in order to get ek as output, and is the hidden state of an is the most important input in order to get this output, right? So somehow if we can provide only those hidden states as inputs that are most important in getting that output from the decoder, then that would have been better rather than providing entire sentence context as input. So this is what attention mechanism is. This was a brief introduction about attention mechanism, and in this video we will also cover its two types. The first one is Bahdanau's attention. Sorry if I'm pronouncing it wrong. And second one is Luong's attention. There is one more type of attention which we call self-attention. We will be covering that in the next video. And that type of attention is used in transformers. But for this video, we will restrict ourselves to these two types. And just taking a pause for a moment, and just to let you know that to make such kind of videos, it takes a lot of hard work, because we don't cover videos like how the videos are there online. We do a lot of research, and I would really appreciate if you could show some love by subscribing to our channel or giving this video a thumbs up. I would really appreciate that. Thank you so much. So, without wasting time, let's dive into attention mechanism. So, I think the brief was clear, right? We don't want to pass the entire context vector. Somehow, if you could pass that information that for getting this output, these are the most important, or for example, this is the most important hidden state. Somehow, if we can pass that information, then that would have been better. So, now let's think about it, right? So, for attention mechanism, what we need as input. Let's say if I am finding this output for egg, right? For output egg, what are the inputs? First input is S1, right? And what time step is it? T equals to 2. At second time step, I am getting output egg. So for T equals to 2, what are the inputs that I want? S1, previous hidden state of the decoder, right? Next, Y1, right? That is the input that we are getting, correct? Now, these were the inputs in encoder decoder. In attention mechanism, we need an additional input, and that is C1. What is this C1? This C1 is called attention input. Attention input. Okay. So the first difference is then that rather than providing the input word and the previous hidden state, we are providing an additional input, and that is attention input inside our decoder celestium. Okay. And since this was at t equals to 2, right? Actually, it should be C2. Okay. So at t equals to 2, we are providing C2 as input, right? So for at ith time step, what will be the inputs that we will be needing? Previous hidden states input. Then we will be providing current time steps input. Actually, there should be two here as well. And one additional input, and that is the attention input at that time step. These are the three inputs that we want. Now the question is, what is this attention input? Let's figure it out. So this attention input is alpha I1 H1. Don't worry what this, I will explain what these alphas are. Alpha I2 H2, alpha I3 H3 plus alpha I4 H4. Or if I can write it in form of summation, then it would be 1 to 4 alpha ij hj. Now, don't worry if you don't know what this alpha is. I will explain everything. So these H1, H2, H3, H4 are clear, I think. These are the hidden states of your encoder. Okay. These are the hidden states of your encoder. This is the hidden state at time step t equals to 1. Right. Same way the other we can interpret the others as well. Now the question is that what is this alpha I1 or alpha I2? These are weights. And what does weight tell you? It tells you how much important the term is. So if I associate this weight with H1, that implies how much important my hidden state at time step t equals to 1 is. Okay. So if this value is very high, that represents that my H1 is very important, right? My H1 is very important, and this is what we wanted, right? What we are doing is that we are not completely eliminating these hidden states. We are not completely eliminating them. What we are saying is that in order to get output as save, this hidden state H4 that is coming from Apple's input, this hidden state is the most important one. So this, the weight that will be associated with this hidden state, that will be the highest, and we are not completely ignoring other hidden states. It's it's just that we are assigning them lesser weights because we want to tell our decoder that this is more important in getting save as output. This is the information that we want to pass to our decoder, right? So now what we will do, that now that we have understood these alpha ij's are nothing but our weights that represents how important our hidden state is. A higher value represents that it is more important. A less value represents that it is not very important. And this importance tells our decoder that in order to get that output, how much important that hidden state is, right? So I hope these alpha ij's are clear. And this alpha ij is called, it has a special name called the alignment score or similarity score. Okay, alignment score or similarity score. It tells how much role encoder's jth time step has on decoder's ith time step output. Okay, now the question is that how do we find it? How do we find it? So for that, we must first understand that what are the terms on which this alpha ij depends, and the quantities on which it depends represents that it is function of those quantities, right? It is function of those quantities. So clearly, if I am finding out weight related to something, then that weight will depend on that quantity, right? So alpha ij is a function of first hj, right? Because it is associated with it. It depends on it. If hj is important, then this value will be higher, right? If hj is not very important, then this value will be lower. So alpha ij is clearly dependent on hj. But there is one more term on which this alpha ij depends. And you know what that is? It's a little confusing, but I will clear it for you. That is si minus 1. This is the previous hidden state of decoder. Previous hidden state of decoder. Now you might be wondering that why my alpha ij is depending on sij. Why my weight that represents how important my hidden state is in giving a specific output, why is it depending on the previous hidden state of decoder? So the reason is actually very simple, because you see here that in order to get this output tape, you must also know that up till now what has been predicted, what we have got as output. You must know that, right? Because to say a sentence, to say something, you there can be 100 ways, right? But what we are actually saying is that depending on the previous output, what should be our next word so that entire sentence is meaningful? What are the patterns that our model has learned? And based on those patterns, what should be the correct word here, depending on what we have got up till now, right? Because to say something, there can be hundreds of ways. But if I have started speaking something, then in order to in order for that to be meaningful, I have to back my next word depending on what I have spoken up till now, right? So same way here, this Sij is important in order to get this Lij. And what does this mean? This means that given whatever translation has happened up till now, how much important Hj is. So because of that given part, how much translation has happened up till now, we are finding out that what is the importance of Hj. So that is why this alpha Ij also depends on whatever translation has happened up till now. It is important. Whatever current decoding context is, that is also important, right? So I hope this part is clear. Now that we know that alpha Ij depends on Hj and the previous hidden state of decoder, how do I find this function? So one approach can be to try every function that is present in this world and see if we are getting it right or not. But that is not the right approach, right? So the people who actually built this mechanism, what they did that they used ANNs. And why did they use this? Because ANNs are universal function approximator. They can approximate any continuous function given that they have enough neurons and enough layers. It can approximate any function. So they are not looking for exact function, but an approximate function that can provide them this value. So rather than manually finding out what the function can be, they used ANN's fully connected neural network in order to find what these alpha IJs are. And the weights and biases in this neural network are automatically learned while we are training our encoder decoder model. Okay, so I hope everything up till now is clear. If you still have any kind of doubts, do let me know in the comment section and I will help you out. Now, one thing that I want to make clear here, that in our encoder model, these LSTMs that we are using, these are actually bidirectional LSTMs. It's okay if you don't understand bidirectional LSTMs. These are mainly used for understanding sentence not only this way from left to right, but also from right to left. We will be covering bidirectional LSTMs and stacked LSTMs very soon. But this was just to give you this information that these LSTMs in the encoder are actually bidirectional. In decoder, we have the simple LSTMs that we have studied in the previous video. These are simple LSTMs. Only here we use the bidirectional LSTMs in the original paper of this encoder decoder model. So now that we know everything about this, let's just understand that how this ANN is actually placed between our encoder and decoder model. So this ANN type, where we have an artificial neural network between our encoder and decoder, this type of attention mechanism is called Bahdanau's attention. We also have another type that I introduced you at the start of the video, and that is Luong's attention, which we'll be covering soon. But let's just now dive deep into Bahdanau's attention and how this artificial neural network is placed between our encoder and decoder. So before moving ahead, just one correction that I want to make here, that here this is actually Y1, and I will tell you the reason behind it, or you must have figured out up till now. This should be actually I minus 1 and this should be Y1, because the reason is that what we get as output from here, that goes as input at the next time step. So this input at time step t equals to 2 is actually output of time step t equals to 1. So since we represent outputs by y, it should be y1. So that is why here it should be s1, y1 and c2, and here it should be si minus 1, yi minus 1 and ci. Now let's move back to Bahdanau's attention. Bahdanau's attention. Sorry if I am pronouncing it wrong or if the spelling is not right. So as discussed, that between our encoder and decoder, we now have an artificial neural network, and we will understand its composition now. So we know that our alpha ij is actually a function of two quantities. The first one is hj and the second one is si minus 1. And then this alpha ij is being multiplied with hj. We are summing it, and then what we are getting? We are getting our ci, right? Now, what will be the dimension of this ci? Exactly what is the dimension of hj, right? Whatever dimension we have here, ci will have exactly that same dimension, right? Now this alpha ij, which is function of hj and sij, what happens that we take these two as inputs. So these are actually vectors. So let's say if this is the first vector, this is the second vector, and this is the first vector, this is the second vector. So what we are actually doing, that we are taking each element of that vector and we are passing them as inputs, right? So how do we write it? We write it this way. This means concatenating. Okay, we are just concatenating these two inputs, right? So this is the input, and then we have a neural network layer. This is single layer which has neurons. You can decide how many neurons you want here. Okay, so we have neurons here, and this is fully connected. This is fully connected artificial neural network, dense layer. Every input is connected with every node of the artificial neural network layer. Okay, now what we are getting here as output is actually EIJ. This EIJ is currently not normalized. It is unnormalized. By unnormalized, I mean that if I consider all the weights for a particular time step, then if this is considered as weight, then sum will not be equal to 1. Okay. And in order to normalize this, we pass it through a softmax layer that finally gives you our alpha ij's. So sum of alpha ij, sum of weights must be 1, right? So that is why the output that we might get from here might not be something that sums to 1, right? And again, the output that we get from here is actually a vector. Now this is the point of confusion that comes in, and I have seen many videos on YouTube not explaining properly that how this is coming as vector when our inputs are single neurons, right? This shouldn't be a vector, right? This should go this way, and then we should get it. How we are saying that this is actually a vector? So we will uncover everything. So the point is that there are two ways. The first way is that you passed hj si minus 1 as input and you obtain your eij, right? So for example, I say here that I pass s1, I pass si minus 1, and I will get my I1. Similarly, when I will pass H2, I will get my EI2. So over loop, I am getting these quantities, and then once I have got all, I will pass them through my softmax layer, and then softmax layer will give me a vector that will be of alphas, right? L one, L2, L4, this way. So I'm passing it through the softmax layer, and then softmax layer is actually normalizing it. By normalizing, I mean that their sum is equal to 1 now. Okay. One way is to do this. You find it one by one through this layer and then do it. But because we have advanced in deep learning, what we will do that we will pass the entire matrix. And how that matrix will look? The matrix will look this way. You will have H1 concatenated with Si minus 1. So exactly what we have here will come here. Similarly, H2, H3, let's say we have 4 hidden states or 4 inputs, then this is how this matrix will look. This Si minus 1 will remain same. You pass this entire matrix, and then the activation functions that we have here are tanh. Okay, the activation functions that we have here are tanh. Yes, I will be making one video on all the activation functions that we have and why do we use these activation function. Everything will be covered in that video. So don't worry. So this matrix will go inside this neural network. Entire computation will happen based on our tanh activation function. And what we will get as output will be a vector of EIJs. Okay. If we have considered 4, then n will be 4. And then this will be passed in our softmax layer, and the output that we will get from there will be our alpha ijs for our ith time step. Okay. So if you didn't understand that how this matrix will be used in computation, so how do we compute when we have a single element? Right? Let's consider the scenario where we are just finding this term. So in order to find this term, what we are doing, that we are concatenating our H1 with Si minus 1. We are concatenating this. We are passing it in our neural network that has weights and biases. So what happens? Aggregation happens, right? Aggregation happens. So here as well, dot product will happen between our weights and our inputs, and we will add biases here. So aggregation has happened. Now once aggregation has happened, we will apply our activation function that will finally tell how much information will pass through the neuron. And in order to understand this, I think the first video that I made on Macaulay-Pitts neuron, that will also help you understand this. It's okay if you don't understand much, but that video will help you understand the basics. Why we multiply weights, why do we have biases, right? So that video will help you. Now this final answer tells you that how much information from your neural network will pass on to the next layer. Okay, so this is what the information we are getting. So what we are getting as output is EIJ. This is for single element. Now instead of passing weights or biases this way, what if we use the entire matrix of weights, entire matrix of biases, and this matrix as it is, and then applying tan h on the entire matrix, right? So this mathematical calculation we do, right? So if we do this kind of mathematical calculation, then what we will be getting as output will be a vector of EIJs. So I think this is clear now, that how we are using matrices, because ultimately this is just mathematical calculation that is happening inside our neural network. So instead of passing single inputs, what if we pass the entire matrix? Then the output that we will get, instead of a single output, we will then get a vector, right? So then this vector is passed in our softmax layer, which again gives output of the final alpha ij's, which are normalized. That means their sum will be equal to 1. So I think this is clear how ANNs are placed. So what will happen, that from our encoder, if I just go up, so from my encoder, this is my encoder. From my encoder, if I am finding out my, uh, let's say, I am finding out the importance of H1 for time step t equals to 2. Okay. Or let's say for t equals to 2, I am finding out t2. So I think there's a lot of mess that I have created here. Let me pause the video and again create this architecture below. I will explain you the details then, because that will be easier for you to follow along. So hold on for a moment. So I have created a rough architecture for you. So what we are saying, that between our encoder and our decoder, we have placed an artificial neural network layer that takes in these hidden states as input, and if we are at time step t equals to 2, then it will take S1 as input. That matrix will go as input inside our neural network layer. We will aggregate the information, then we will, since we have tan activation function, so that aggregated, we will apply tan operation on that aggregated information, and that is the information that our neural network has finally passed on to the next layers. Then we have a softmax layer, because the outputs that we are getting from here, the vector that we are getting from here, is actually not normalized. The sum of the numbers, or the sum of the elements of this vector, is not equal to 1. That is why we pass it through the softmax layer. And because of softmax activation function, the final vector that we get has elements whose sum is equal to 1. And that vector that we get is actually the weights at time step t equals to 2. And then this plus sign that we are seeing here, what we are doing, that we are taking our hidden states, we are taking the corresponding weights that we have got here, we are doing dot product of them. So if you got the vector like hi1, hi2, since time step is 2, so it will be 2 1, 2 2, 2 3, 2 4. And if we have 4 hidden states, h1, h2, h3, h4, then this c2 will be equal to alpha 21 h1, alpha 22 h2, alpha 23 h3, and alpha 24 h4. This final c2 will then go as input inside our encoder along with S1 and Y1, and it will help you predict what our next word will be and what will be the corresponding hidden state. Okay, so ये है कि after ये है, we will get A as output, and we will get S2 as output. This is the hidden state, and this is the final word that we have got. Two recommendations here. If you don't understand these weights, biases, aggregation that is happening here, I would recommend you to watch my first video on Macaulay-Pitts neuron. That will help you get a basic idea. And second is to go and watch encoder decoder video, because this video is actually in continuation to that video. So please watch these two videos to fully understand this part. But still, if you have any doubts, do let me know in the comment section and I will help you out. So this was Bandhanau's attention, where we have an artificial neural network layer, and through this we are passing the information that which hidden states are most important in finding out the output at that time step. Okay, I think this part is clear. Now let's move to the next type of attention, and that is Luong's attention. Luong's attention. This is actually very simple, and you will really appreciate that how much simplified they have made everything. So previously, what we were saying that alpha aj is function of si minus 1 and hj. And then we were saying that in order to find this function, we are using artificial neural network. And in that artificial neural network, the vectors that we are getting out from there, we are then passing it through the softmax layer. And if we go into the mathematical part of it, then we discussed what EIJ is, right? That was actually tan h of the weight that we are considering SI minus 1, HJ plus the bias. Then from this, we calculated alpha ij, which was which was actually output of softmax layer. So softmax function is actually this summation of whatever alpha ij's you have. Let's say you have h or n HIJs, so that will come here, exponent of EIK. And then from this alpha ij, CI was calculated, which was summation alpha ij HJ. And this alpha ij is, it has its own weights and biases. Okay, because that is also a softmax layer, right? Where we have softmax as activation function. So this part is clear. This was the mathematical part. Now for Luang's attention, it simplified everything. It simply said that why are we getting into the complexities of finding out this function? It completely changed the scenario by saying that in order to find out alpha ij, just find out that what is the dot product between our SI and our HJ. Now you would say that what really happened? Why dot product? So to understand this, think it this way, that what does dot product tell you? It tells you that how much similar these two vectors are, how much aligned these two vectors are, right? If the dot product is high, it's a big number, that represents that these two vectors are very similar, right? They are very much aligned. But if this dot product output is a very small number, that represents that these two vectors are not similar, they are not at all aligned, right? So if in the vector space I consider these two vectors, then they look very similar, right? Their dot product will be high. But if I consider this vector and I consider this vector, then they are not very much aligned, right? So their dot product will be very low. So that is why this dot product actually tells you that how similar these two vectors are. And once you know how similar these two vectors are, we are equating that to our alpha ij's. And why we are putting it equal to alpha ij's? For that you need to understand that what alpha ij's represents. We already discussed that, right? What alpha ij represents. It represents that how much important are HJs, how much important our HJ is in calculating the output at that time step. And what is the output at that time step? SI, obviously, even the word that you are getting as output, that is also based on SI, right? Because if I just go down here to the decoder's architecture, then you are at time step t equals to 1, you are getting S1 as output, right? And this S1 is then passed through softmax layer in order to get this specific word as output. So in reality, the output is SI only. So if we are at time step at equals to 1, then the output is S1. So that is why I'm saying that here this alpha ij represents that how much important my hidden state is in obtaining the output Si. And why am I finding out their dot product? Because that tells how much similar our output and input are. And if they are very similar, that means the importance of our input is higher, right? Because in order to calculate your output, your input must be aligned with it, right? It will be a function of it, right? If it will not be a function of it, then you will not get correct output. So that is why if these two quantities are very similar, by similar I mean aligned, then that means that our input carries more importance in giving this output. And that importance is nothing but R alpha ij. So what we are saying that instead of having a separate artificial neural network layer and then using back propagation to find out its weights and biases, which is very tedious task, it's better that you use a reverse approach where you are doing a very different thing. Actually, it's a little contrary to think about, but what we are saying that in order to find out your weights, you find out how much related your input and output are. If they are very much related, that means input played a major role in producing that output. And since input played a major role, that is what we are saying that it is equal to our importance or our weight, and we are equating it to the dot product of our input and output. And the product that we will get from here, again, that will not be normalized. So that is why we will pass our vector r alpha ij. Actually, this is a single value. We will pass our alpha I vector like alpha I1, alpha I2. We will pass our vector inside the softmax layer. It should be actually E. Then the output that we will get will be the final weights. That will be our final weight. So basically we will normalize this so that the sum is 1 because dot product can be anything. 4, 2, it can be anything. What we want is that our sum of all the elements is 1. So that is why in order to normalize it, we will use a softmax layer. So this is what Luong's attention is. And one more thing. Now that we are already using the current output, we will not pass our CI one as input here because we have already find out our output. Why will we be providing it as input if we already know what our output is, right? So what we will do that instead of providing it as input, we will concatenate it with our S1 and then we will pass it in our softmax layer. So this SI, the output and the attention input that we have got, which is nothing but sum of our weights and hidden states. This concatenated value will be passed through our softmax layer in order to find out the final word. Actually, this will be a vector again of probabilities, and we will pick the highest probability, and the corresponding word to it will be the final output. Okay, so to summarize again, instead of having neural network layer and then finding out the weights, in like in Bahdanau's attention, what we are seeing in Luong's attention, that replace that artificial neural network layer, and in order to find out weights, simply find the dot product of our output vector, output hidden state, and our input hidden state. If they are very much similar, if they are very much related, if they are very much aligned, then our weight will have a higher value. If they are not related, then our weight will have a lower value. And if two things are related, that means one had a strong influence on it, right? That is why we got that value. And that is why our weight is high. Why? Because it our input carries more importance in finding out that output. That is why. Okay, so that is why we are using the dot product. And what we are doing, that we are then passing this to our softmax layer in order to find out the normalized weights, which are then multiplied with our hidden state of encoder in order to find out our attention input. This attention input is then concatenated with SI directly because we have already got our output. And then this final vector is passed through our softmax layer in order to find out this final words. Okay, so I hope this video on attention mechanism cleared all your doubts. If you still have anything, even the slightest doubt you might have, do let me know in the comment section. You can also reach me out on my LinkedIn profile. I am there on LinkedIn with the same name that I am with on YouTube, Coder Says. And you can also reach out to me on Instagram, again with the same name, Coder Says, with the same DP. I will be happy to help you. If you like this video, give this a thumbs up and don't forget to subscribe. In the next video, we will be covering self attention. So stay tuned and thank you so much.